the deflection equation is m over EI. In each and every one of these are separate chapters in the next class. How many mechanicals? You're going to EML 3500. You're going to see these equations. How many civils? You're going to go to EGM 3331. You're going to see these equations. Okay? The rest of you are probably industrial. You won't see these damn equations. So, in each and every equation, there is a stupid I thing in here. I may not know a whole lot about I right now, but I do know it's in the denominator. So if I want the deflection to get smaller, my stresses to get smaller, what should I do to my I value? Make it as big as I can, because the bigger it is in the denominator, the smaller each of those elements gets. So the objective is create a huge I value. The one figure that creates the largest I value is the I-beam. The I-beam is an engineer's wonderful play toy because it by itself creates a large I value. Now, what is I? What is I? It's a stiffness parameter. And you can't say I without saying axis. So you can't sit there and say, I is 300. 300 about what? The centroidal axis, the base axis, the x-axis, the y-axis, the z-axis has got to be about an axis. So you must specify. Okay? You can't just say 300. Can I borrow you two? Come up here. Come on. So what is this I? We're going to show you physically what this I is and why axis matters. So we're here, so you're going to grab one end. Grab one end, please. Grab the other end. Put it up a little higher so everybody can see. So I apply a load. Hold it tight. No, don't give me that. Hold it tight. I apply a load. What do you see happening? It bends. Right? It deflects. Now I take the same piece and I'm going to turn it onto this axis. Okay? Different axis. Hold it tight because I'm about to put a load. So I am squeezing way harder than what I do. Do you see the bend? It is much stiffer on this axis than it is on that axis. I just demonstrated I for you. Thank you. Give a round of applause. Everybody get it? So when I tell you, hey, the I value is a stiffness parameter, notice it was very weak on this axis, but very strong on this axis. So if I'm going to load this thing up, I'm going to put it like this, and then load it up because it doesn't deflect as much. If I load it this way, you saw the bend. That's not what I want. I want the stiff portion. So, that gives you a demonstration of what I really is. And every structural equation has I in the denominator. So I want to make I as big as possible. The bigger the better. And one way to achieve big is to use a I-beam for several reasons. So, there are two stiffness parameters in engineering. This is in the videos. I'm not saying anything that's not in the videos. How many have seen this video? Not everybody. That's not good. Because I'm moving. I told you we would be moving. We're moving quickly. So there's two stiffness parameters in it. One is Young's modulus of elasticity, given the letter E. That's a stiffness based on material. So steel will have a different E value than bronze, than aluminum, than concrete, than wood, etc. They each have their own E values, modulus of elasticity. I I is another stiffness parameter based on the geometric shape. So a 2x4 is going to have a different I value than a T shape or a I. Right now, they're building a new apartment complex for student housing right next to the Standard. Everybody know where the Standard is? Very close to Panera Bread. Go down that road, you'll see there's a whole new complex going up. If you look at the shape, overall shape of the beams being put in, they look like this. What it is a double T. That's a single T. Put two of them together, it's a double T. Each one of these, and it's made out of concrete, each one of these is about 51,000 pounds. Going up as floors. Each of those I-beams are about 51,000 pounds. Why did they choose this shape? I don't know, the engineer chose it because part of it is it kind of resembles a I-beam. Probably the span was pretty big, so it needed a little more support. But I'm sure he has got reasons for it. But I thought you should see it. Go by it, take a look. I got a huge crane pulling these guys in and putting them in as floors. All right, definition. All three of these definitions say the exact same thing. What is I? I is the stiffness of the section, of the shape. So when you go to the next class, you're going to have a beam, and it's going to be some sort of beam, and you're going to have a load, and right next to it, you're going to have the actual look of the section, and it'll give you dimensions and so forth. So this beam, we never gave it a shape in this class, but in the next class, you're going to give it a shape. So you're going to see the beam with its loading, and then you're going to see a section of what the beam looks like. So this would be a T-section. So what we're saying is the I measures the stiffness of that section. Another way of saying it is a mathematical concept. So we human beings want to put a number to everything. We got a speed, we put a number to it, 60 miles an hour. Acceleration, 10 feet per second squared. We want to quantify just about everything we can. So this is our way of quantifying the stiffness of a section. Notice what it says, a mathematical concept used to quantify, to give something a number that shows its ability to resist bending or buckling. Number three, a shape factor. And this one I like because it's a shape factor that measures the relative location of material. That's why you need to specify an axis, because the eye is telling you how much material is surrounding that axis. Okay? Again, how effective is it in resisting bending? All three things, all three definitions say the same thing, just said it differently. That's it. How do you calculate I? Simple. Calculation of I is right there. I x equals integral y squared dA. I is equal to integral x squared dA. Now, if you're reading the textbook, you'll see Hibbler write one subscript. It will write IX or IY. I use two subscripts. Why? Because down the road, not in this class, but down the road, you're going to see products of moments of inertia. When something is not symmetric, you're going to be able to calculate the products of moments of inertia. So here you'll see an IX, and then, you'll see a Y, or an XZ, or a YZ. So that's why I tend to use double subscripts instead of one subscript. So if you're reading Hitler, Hitler writes one subscript, I write two. Just so you understand the difference. Now, are we going to do integration? Well, of course, just like centroids, you can do direct integration, or you can do composite bodies. We are going to do composite bodies. Because outside the real world, when you lead this, I doubt your entire engineering career you're going to do an integral. I doubt it. If you do, you're going to blame the architect because he gave you some fucking figure that he or she developed out of the blue to make it look cool. Right? But most of the time, you're not dealing with cool shit. You're dealing with pretty much standard structures. So you won't be integrated. You may do composite bodies, for sure. So these same equations, composite body, notice the integral becomes summations, and the dA becomes A. So we're going to do composite bodies, just like we did for centroids. All right? Couple of notes to keep in mind. Number one, no accurate physical analogy for or description for I. We made this shit up. Why? Because we're deriving structural equations and kept us getting this integral. Integral y squared dA, x squared dA. And we're like, what the fuck is that? Well, we gave it a value. We said it was I, and it measures stiffness. Period. End of discussion. We made it up. That's it. Number two, I already said this. You can't describe I without saying axis associated with it. So you have to have the coordinate axis involved in order to describe I. Okay? Number, whatever, A. So, look at it this way. You're looking at y squared dA, x squared dA. You're taking a distance and squaring it. So if I can make that distance further and further away from the axis, it's going to contribute a huge amount to the I value. That's why the I-beam is so significant. Because if this is the axis in question, notice I got a ton of area further away from this axis. That is the beauty of the I-beam. For any given size, it creates probably the largest I value you can create. That's why engineers love the I-beam. Okay? The I-beam is used a lot because of that. But not only that, here's an additional piece of information that you're going to find when you go to the next class, is that the I-beam is special because these guys are called the flanges. And they carry 95% of the bending moment. You know that M that you calculate using shear bending moment diagrams, that M, that's being carried by the two horizontal pieces of the I-beam. This guy right here is called the web and carries 95% of the shear. That's that V crap. So it's pretty nice because it separates out the bending moment from the shear and puts it at different locations on the section. That's another huge advantage for the I-beam. Okay? Huge. Monstrous. As a matter of fact, I'll give you a story that happened. I have a friend. Yes, I do have friends. He sold, I forget what it was, if it was LensCrafters or VisionWorks, one of those. It was an eye doctor. Sold it. Made a ton of money. Lives in Cheval, or bought a house in Cheval. His wife, he calls her Goddess. If you look at his phone, and she's calling him, it rings Goddess. It doesn't say her name, it doesn't say wifey. Goddess. Whatever. Goddess decides, I don't like this. I have this beautiful panoramic view of the pond, and I have this fucking pole sitting in the middle of it. I want it out. Honey, I don't want this. So he calls an engineer. The engineer comes in and says, I can't do it. What do you mean you can't do it? I can't eliminate this bar here. The span is too long. He did not like that answer. So he calls me, he says, hey, I talked to an engineer. The engineer says he can't put this, can't eliminate this bar here. I have a 24-foot span or something like that. I'm like, I'll get back to you. So I looked up my shit, went to the steel manuals, and I called him back and said, the engineer's right. He cannot sign off on this. Cannot be done. Because it sits outside the realm of the beam. And he goes, well, can I really do it, or is it impossible? I said, nothing's impossible. Okay, tell me how to do it. I said, I can't sign off on this. He goes, I know. I'm still going to do it. I'm like, really? I said, we can put an I-beam in there, but in order to get that I-beam in, the size of the I-beam to take care of that is going to be a monster. I'm telling you right now, you can't put it in. Because what do you mean I can't put it in? I said, how are you going to get it in? The only way to get it in, I said this, and I said, the only way to get it in is to knock out that wall, which is a perfectly good wall, to slide the beam in. He goes, okay. I'm like, you're going to destroy a wall? He goes, yeah. I'm like, are you shitting me? He goes, no. Just tell me the size, I'll go get it and put it in. I said, wait, you're going to need a massive crane to get this sucker in. He goes, yeah. I said, also, because you're modifying it, an inspector has to come in and inspect it. He goes, yeah. I said, yeah? He goes, yeah, don't worry about it. I said, okay. I said, you know this is ridiculous. He goes, you gotta understand, he has so much money, he goes to Germany to buy his BMW. He doesn't buy them over here from a dealership. He goes literally to Germany to pick out everything he wants in the car, to ship it back here to drive it. That's like money just flowing out of his pocket, you know? Anyway, so I picked out a beam. He puts it in. He calls me. He says, come to the house. I'm like, okay. So I come to the house. There's a fucking panoramic view of it. I look up, I'm like, the beam's up there? He goes, yep. I'm like, how the hell did you do this? He goes, don't worry about it. I said, the inspector came? Yeah. And he signed off? Yeah. I'm like, I don't want to know. I don't want to know. So now we have a running joke. Hurricane comes. He calls me up. Every hurricane, he calls me up. He says, want to come to the house? We can sit underneath the I-beam. It ain't going anywhere. I said, you're right, it's not. So what I did was I put a massive motherfucking I-beam in there to bring all the stresses down. He didn't care how much it cost. He didn't care what the size was. He didn't care about anything. And I said, how'd you get the inspection? No, I really don't want to know. I don't want to know how you got the inspection signed off on. I don't want to know. No, I don't want to know. He goes, I just want to thank you because it works. I'm like, of course it works. I told you it would. But nobody's going to sign off on it. That's why the engineer told you it's not possible. Because he can't sign off on it. Because it's outside the realm of the steel manual's code. You got to go by code. Because nobody's supposed to sign off on it unless it's code. Obeys the code. Well, all this shit didn't obey any code. That's why nobody's going to sign off. Hey, I don't know what he did. All I know is it got done somehow. I have no idea. La 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 la. That's all I said. All right. Moments of inertia. I'm repeating myself again because it's very important. It really consists of an area and the position of the area with respect to an axis. So an eye about the centroid is going to be different than the eye about the top of the beam or the bottom of the beam or somewhere in the middle. They'll have all different eye values. Weird, but true, moments of inertia are always going to be positive. Why? Because you're squaring x, you're squaring y. It cannot be, the overall number cannot be a negative number. Fifth, units, weirdest units. Why? Because it's some length raised to the fourth power. You got x squared, that's feet squared, times an area, which is also feet squared. Feet squared gives you feet to the fourth power. Unusual units. Again, why so unusual? Because it's trumped up. We described this, we made this shit up to describe our world better. Two eye values that are going to be important. And those are what's known as the principal axes, or principal eye values. Those are usually about the centroid. So usually, when you calculate I, it's usually about the centroid, whether it's the y-axis that goes through the centroid or the x-axis that goes through the centroid, it's still usually about the centroid, the centroidal eye values. All right, radius of gyration, another trumped up number that we human beings made up. What is the radius of gyration? Notice, here's the definition. Location at which all the area can be concentrated from a particular axis with no change in the eye value. So I have some area. This is the LL axis. What the radius of gyration is saying is take the LL axis, concentrate this area here, a distance RG, or sometimes called K. So it depends on what textbook you read, sometimes called RG, sometimes called K, for the radius of gyration. Okay? That's what the radius of gyration is about. How do you calculate? Because it's not something you can experiment, it's a calculation. And the calculation is very simple. K, or R, is the square root of I, XX over A, or it could be I, YY over A. Because I value is always some sort of distance squared times an area. If you rearrange this for K, a distance, you're going to get this. So a radius of gyration, if I ever ask you for a radius of gyration, it's a calculation, square root of whatever I value you're looking at divided by the total area. Okay? Where does this come into play? When you're designing columns. In next class, there's a whole chapter on columns. And you'll see the equations have R in it. Okay? What is a couple of notes on the radius of gyration? It has units of length. Because you're taking the square root of feet to the fourth divided by area to the fourth. That leaves me a length to the squared, and you take the square root, you're going to get length. It's not a distance that has any clear-cut physical meaning. Again, we made this shit up. Third, values only determined by computation, not by experimentation, not by observation. You have to compute it. Okay? Next important thing that you're going to need is what's known as the parallel axis theorem. The parallel axis theorem is a transfer theorem. It allows me to shift the eye from here to another axis, but the axes have to be parallel to each other. So I can shift it from here to there. Okay? It is a derivable equation. I'm sure Hitler does a fantastic job at deriving it. It's really like 3 lines and you're deriving it. It's not a long derivation. But it literally says, I about some axis that you're trying to transfer to is equal to ICG plus AD squared. ICG, that is the I about the centroid. A is the total area, and D is the distance between the two axes. Now, it is very important you understand something. This says ICG. It's very specific in what it says. So I can say IX prime is equal to ICG plus AD squared. Yes. I cannot say IX prime equals I about some axis A plus AD squared. That's a big no. It is very specific in that you have to go through the center of gravity. I cannot just arbitrarily send I values from one axis to another without going through the CG. This is a scalar equation. So I can rewrite this as ICG is equal to IX prime minus AD squared. So if I want to transfer from, let's say I know the I value about the X prime axis. If I want to transfer it to the CG, I can use that equation by subtracting AD squared. I can get the ICG. And you're going to do this a lot. A lot. How is this used? Well, here's one way. If you look at your textbook, good old Hibbler gives you I about the x-axis, I about the y-axis. Remember, he uses one subscript, I use two. He's saying the I about here is pi r to the fourth over 8. He never gives you the ICG. In other words, he does not give you the I that goes through that axis. In other words, the I through this axis that goes through the center of gravity or the centroid of the figure, he doesn't give you. Why? I have no idea, because that's probably more important than that one is. How did he get this? Somebody sat down and did the integral for a semicircle. Now, I'm going to use the parallel axis theorem, and I'm going to transfer to the center of gravity. Here it is. ICG equals IX minus AD squared. What's the formula that is in the back of Hibbler's textbook? Pi r to the fourth over 8 is I about the base of the semicircle. Minus A. What's the area of a semicircle? Pi r squared over 2. What's the distance between x-axis and the centroidal axis? Well, he gives it to you as 4r over 3 pi. That's given to you. So if I dump in 4r over 3 pi and square it, and then do some algebra, I'm going to get this, 0.1098r to the 4th. That's the I value. Notice, the I about the base of that semicircle is pi r to the 4th over 8. The I that goes through the centroid but parallel to that straight edge of the semicircle is 0.1098r to the 4th. Remember, wherever you are, there's a different I value because the axes are going to be different. Okay? That's why I say to you, you can't just say I is 100 or 300. What axis? Similarly, this is for a quarter circle. ICG equals IX minus AD squared. In the back of the book, he tells you IX, in other words, about the base of the quarter circle, it is pi r to the 4th over 16. Again, somebody did the integration for you and came up with the formula. Minus A, quarter circle is pi r squared over 4. And the distance happens to be the same, 4 over 3 pi. Mishmash these numbers and you're going to get 0.0548887, somewhere in there, r to the 4th. So I've just used the parallel axis theorem to transfer from the base of a semicircle and quarter circle to the centroid of it. Yes? Now, if you look closely, I gave you a formula sheet that was in Canvas, and I've already told you, please download it. This is the formula sheet from Hibbler. Nowhere does he have the I that goes through the centroid. He does not give you that. Nowhere is it given. However, in the sheet that I gave you, notice I give you, in this sheet, let me blow it up a little bit. Notice I give you the Ix and Iy, but I also give you 0.1098 R. So an I with a bar on it is the I that goes through this axis. That's the XX. 0.1098 R to the 4. That equation is not given to you by Hibbler. But this sheet that I'm going to have that is on Canvas and that you will have during the test does have it. Same thing with every other configuration. Here's the quarter circle. The I that goes through the centroid, 0.05488 R to the 4. For the rectangle, somebody sat down and did the integration. I about the base right here is BH cubed over 3. But the I that goes through the centroid is BH cubed over 12. Big difference. There is a difference. Okay? Everybody see that? Now I want you to note here is how you would do integration. Let me zoom out a little bit. So here is integration. I'm going to say Ixx is equal to integral y squared dA. That's the formula. Okay, so I'm going to create a little strip right here. I'm creating a little strip. I'm calling the height d8 dy. The length here is b. So it's y squared, and I'm writing dA. dA for this little elemental strip is dy times b, or b times dy. And then I'm going to integrate this from below the x-axis minus h over 2 to h over 2. If I do that, I'm going to get by cubed over 3, and I evaluate this from minus h over 2 to h over 2. Notice, I get what's in the formula sheet, bh cubed over 12. And that's how you do all of these. There's somebody sat down and did the integration for you and gave you a table of common shapes and their I values. I just did it for the rectangle. But, most important, and this is the most important fact right here, the cubed length is always the distance perpendicular to the axis. Notice, I'm doing the XX. This distance is perpendicular, which happens to be the h. That's what's getting cubed. If I were to do this guy right here, that would be the y value. What's perpendicular? B. So now, instead, Iyy would be hb cubed over 12. So the important factor is the quantity that's being cubed is going to be the distance that is perpendicular to the axis in question. Okay? So if you look real closely, here is the triangle. I have Ix about the centroid. That means through here. What's being cubed? Well, this is the axis, so that distance is being cubed. That's got to be h. There you see bh cubed over 36. If I do it about the y, then the b is going to be cubed. And you can see b cubed h over 36. Do you understand what's being cubed? Because that's important. All right? So this is the derivation of these formulas, or how you would derive it. It's something you did back in Calc 1. You created little strips, you gave it that height, you gave it a base, and then you plugged it in and integrated. Ain't nothing fancy. So this was done back in good old Calc 1, really. Last thing before we get to the problems is, there's also a perpendicular axis theorem which says, hey, if you know IY and you know IXX, then you automatically know what the IZZ is. It's just the sum of the two axes. So you know IYY, IXX, you know IZZ. Pretty easy. Got it? Now, I told you to please download this sheet that's in Canvas. This is going to be your centroid calculation. The bottom piece is going to be your area moment of inertia calculation. Yeah, I'll get it right back. If you look real closely in this table, what you'll see is ICG and AD squared. The second column is ICG, the last column is AD squared. What do I really have there? I have the parallel axis there in my diagram, in my chart, in my table. If I take and add ICG plus AIDI squared, that is the parallel axis there. And eventually, notice I sum these two, and then I'm going to add these two together to get ICG XX or YY or whatever it is. You with me? So in the table is the parallel axis there. Now in between the second and last column, those are just my convenience to get to the last column. I need an area, I need a DI, the distance between axes, and I need to square it. So these three columns, 1, 2, 3, are just for a convenience more than anything else. The columns that I really need are this one and this one. Okay? You with? Again, you're going to have this as one of the pages on the test. You're going to have this as one of the pages on the test. When you get the test, you will yank these two off so you can have them handy dandy as you do the problems. All right? So bring a stapler with you. And I'll have a stapler in case you did bring a stapler so we can staple everything together at the end. And I don't want the formula sheet, so you can keep that. I'd keep it for the next class if you have to take the next class. All right. Let's look at problems. The first problem, this one. Well, I already showed you the integration, right? I told you we're going to create a little here. We're going to call this dy, that's going to be b, and I showed you the integration. I'm not doing this problem. Next, we're going to do this one. Now, every problem I've done for centroid, I'm going to repeat for area moment of inertia. Why? Because that's what you're going to do in the next class. You're going to have a shape, a section, and you're going to find the centroid of that section, and you're going to find the area moment of inertia of that section. So we're kind of repeating so that you can see how everything fits together. Notice it says, find me the area about the centroidal axis. So somewhere in the centroid, we calculate the centroid to be here, and we call this the datum. And we said this distance, if you go back and look, was 100 inches from the base. That's what we said the centroid lies at. You remember us doing this? Okay. And what we did was we said, hey, and it doesn't change. Once you do it for the centroid, it stays the same for the area moment of inertia. We closed this up when we said, hey, this is area 1, this is area 2. Okay? So what I'm doing is, in essence, saying, hey, I have this, plus I have this, to get to that. That's what I'm saying. I'm superimposing a horizontal and a vertical rectangle to get to the overall field. All right. So I'm going to create my little table component. So that's why you'll have the table with you. You don't have to create this. ICG area DI squared AI DI squared. This is summation of this. This is summation of that. Nope. This component is area 1. This is area 2. We start with something simple. Now, from the centroid, we calculated the areas. Copy paste. You love to copy paste. You don't go a day in your life without copy pasting. Right? Copy paste. So we found this area to be 4,800, 4,800. For a total here of 9,600. That's what we found from the central. Now I don't really need to find that summation, but I put it in there so you can see it. I'm going to calculate the I values. So the ICG XX of the first element, that would be this one, 112 BH cubed. You can look it up in the formula sheet. That's going to be 112 times B. Now remember, what's the perpendicular distance? This is the perpendicular distance right here. Which means I gotta cube the 120. So this has got to be 40, which is the base, times the 120 quantity cubed. If I were doing the y, I would be cubing the 40, right? If I was asking you, hey, tell me I, y, then this would be the axis in question, and I would be cubing the 40 rather than the 120. This is going to give me 5.76 times 10 to the 6th. ICG XX of 2. That's 112 BH cubed again. Now, this is the axis through here. This is what's being cubed, which means I'm cubing the 40 now. That's 112 times 120 times 40 quantity cubed. That's going to give me 6.4 times 10 to the 5th. Sum this column up, I'm going to have 6.4 times 10 to the 6th. That's the ICG of each individual piece. In other words, what I just found was the ICG that goes through this axis. This right here is my 6.4 times 10 to the 5th. Here, this is my 5.76 times 10 to the 6th. So I just found the I that goes through the centroid of each piece. Everybody understand? I did not find the I that goes through the centroid of the overall shape, which is composed of 2 rectangles, one horizontal, one vertical. I haven't done that yet. I just found each individual one. I already have the area, I need the DI. Okay, well, what's this here? What is that distance from the bottom to the center of this? What is that? Well, it's half of 120, which is 60. But where is my actual centroid of the overall figure? It sits right here. So what I need is the distance between the axis here and this axis. That's my D1. What is that distance? Huh? What is that distance? I keep hearing 40. Are they right? Is it 40? That would be 40. Square it, 1600. Multiply this times this to get this number. 7.68 times 10 to the 6. Do the same thing for this one. What's the DI of this one? Well, I got to go from here, which is the centroid of that figure, down to the centroid of the oval. What is that distance? That would be D2. What is that distance? From the centroid of the horizontal down to the centroid of the overall figure. That is also 40. That's 1600, which gives me 7.68 times 10 to the 6th. Add this. That gives me 15.36 times 10 to the 6th. Add these two together, I will have ICG of the overall figure about the XX axis to be 2.176 times 10 to the 7th inches to the 4th. Remember, the units are length raised to the 4th power. Oddball units. Oh, yeah. Everybody got that? Who don't got it? Now, where am I going to get you? Where are the common errors? What does Noah look for when he grades it? I'm going to tell you. 1, you picked the wrong formula from the formula sheet. Well, that sucks. Error number 1. Error number 2, you forget a minus sign. Because if I give you a cutout, that's a negative area. Gotta take that out. Error number 2. Error number 3, your DI suck. The distance between the axes in question you get wrong. In other words, you didn't give me the right DIs of 40 and 40. What are those DIs? That's the distance between where the centroid of one and the centroid of the overall are at. That's the DI I'm looking for. The centroid sits at 100 inches for the overall figure from the base. The centroid for the vertical sits at 60 from the base. So now I need a DI that goes the difference, right? Those are the 40s. Any questions on this? Yeah?
Can you show me?
Oh, the other thing that you fuck up is you add it wrong. You just simply add wrong. Everything right except these numbers aren't right because you put into your calculator wrong numbers. Or you forgot to put a negative sign and you got the wrong number. Yeah?
Can you show me how you got D2 again?
Huh?
Can you show me how you got D2 again?
How I got D2?
Yeah.
Well, this distance right here is 20. Would you agree? Half of 40 is 20. This whole distance is 120. This distance has to be what? Well, this is 100, that's 120. This distance is, the difference is 20 plus the 20 is 40. Right? So this is 20. So the entire distance from the axis of this to the centroid of the whole figure is 20 plus 20, which is 40.
Thank you.
Yeah.
Earlier you said you couldn't have negative movements. If there was a hole.
You can't have this being a negative, the overall value. These individual pieces can be negative, but the overall value cannot be negative. So if you sum this up and you get a negative, you know you did something wrong. Let's take a look at this one. This one, we did the centroid of. We measured from the datum dot at the bottom, is where we put datum, to here. We said that distance was 3.8 meters. If you go back to the centroid, we calculated this. And notice it's asking me, hey, tell me the I value that goes through the centroid, the XX. Okay. We know there's an axis of symmetry. We know that. Here we go. We broke this up into 1, 2, and 3. 3 is a cutout. So component, ICG, area, DI, DI squared, AI, DI squared. I'm going to sum this column. I'm going to sum this column. The components are rectangle 1, rectangle 2, the vertical, and then a triangle, which I know is a cutout, negative n. Negate, 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 negate. All right, let's calculate this first column, ICG. ICG XX of 1. That's going to be 112 BH cubed. Well, I'm looking and calculating the I that goes through this axis right here. What's going to be perpendicular? It's going to be that, which in this case happens to be the 2. That's 112 times 6 times 2 quantity cubed. That's going to give me 4. ICG of 2. That's going to be, again, 112 BH cubed. That's 112 times, B is 4. H, here's the I. This is the perpendicular. The perpendicular is to the height, which is 6. Quantity cubed, that gives me 72. For the triangle ICG 3, look at the sheet. You can see it. I'll bring it up so you can see it. 1 BH cubed over 36. So I'm going to write 136 BH cubed. Again, this is 136 times the base 4. What's being cubed is the 3 because this is the height, 3. That's going to give me a negative 3. So important you don't miss this out right here. That's huge. Because now this is going to give me a summation of 73. Now, area, we already know what the area is. Right? From the centroid, I'm going to copy paste. Those were 12, 24, minus 6. If you don't believe me, go back to the centroid calculation and check it out. Because those were the areas we got. Okay? Now I need DIs. So from this to here, that's going to be D1. So from the axis that goes to the centroid of the first shape to the overall centroid is D1. What the hell is that number? Huh? What'd you say? 2.8. How'd you get that? Pull that number out of your ass? Perfect. Your ass is very smart.
I took the center of the bottom. and
Which was,
the rectangle
what is that number?
of one from the bottom.
Right?
Uh,
And then subtracted it from 3.8.
yeah.
Exactly. So notice, he's got to take half of 2, 1. Subtract from 3.8 to get the 2.8, which is DI. So DI here is 3.8 minus 1/2 of 2 in essence, which in this case is 2.8. I gotta square it, 7.84. I gotta multiply it, notice how I use my fingers. You don't know how many times I get people multiplying these two numbers together. No, it's this number and that number to get this number, 94.08. What's the DI of 24? Or the horizontal, the vertical triangle? Huh? 2.2. Notice where errors are creeping in. What did I tell you? One of the errors is always going to be your DIs. You'll fuck those up. It's first place, one of the first place. So I look at this, so if this is my table that I'm grading, I instantly look at this number. If that number isn't 73, I know either one of two things happened. You picked out the wrong formula, or you forgot that negative sign. Quick look, you got 472 and 3. Then I automatically know you missed the minus sign if you didn't get 73. That's the first look. Second look, I'll look right here at this column. Do you have these numbers correct? If you don't, then you did not find the DIs properly. I already got a value of 2.2. Wrong. 2.2 is not right. That's the next source of error. It is not 2.2, it is 1.2. 3 minus the 1.8. Square it, 1.44. Multiply these two numbers together, 34.56. And then the DI for this guy is 0.8. Multiply these two, or square it, 0.64. Multiply these two, you get negative 3.84. Sum this, 124.8. Now you sum these two together, and you'll have the ICG about the x-axis is equal to 197.8 inches to the 4, or actually it's meters. Meters to the 4. Now, where is the source of error? The source of error is that DI. The distance between the axis that goes through the centroid of the individual piece to the centroid of the overall figure. There's where you're going to have a mistake. Now, I've got a surefire way where you don't make that mistake. Here it is. Let me show it to you in a little bit of a diagram. And the reason I came up with this is because I was making the same mistakes you were. I'm like, fuck, I can't get the DIs right. So I gotta find a way that I can do this easy. Here's the easy part. So you know you have the centroid. This is the centroid. Area and Y bar. So I'm going to copy this and this into here. We're going to copy paste area and Y bar. Here's what's happening. I'm not doing the calculation about the centroid. I'm doing the calculation about the base. When I do that, my DIs are all going to be my Y bars. And if I were doing the Y-axis, I would do it about the y-axis, which means all my distances will be X bars. Oh, I don't have to sit there and say, half of this number subtract from that number gives me the DI. I don't have to do that. All I do is copy paste. I love copy paste, don't you? So I'm copying and pasting the area plus the y bar. Then I square the y bar, then I multiply. Literally, this table takes almost no work at all. And then I add these up, add them together, and what I have is I about the base. Well, I didn't ask you for I about the base. I freaking asked you I about the central. Now I'm going to use the transfer theorem to transfer it from the base to the centroid. So I'm going to say ICG, which is what I'm looking for, equals I base minus AD squared. Well, what the hell is that D? From the base to the centroid of the overall figure is actually my y bar that I calculated in the centroid calculation. Nowhere did I have any kind of math error here. The only error is if you fucked up the y bars in your centroid. Now you got a problem. But if you didn't screw those up, there is no screw up here. So this will eliminate your DI mishaps. You with me? So I'm going to send everything to the base and then transfer it up to the centroid. If you look, can I see the testing manual? If you look at the testing, I'm actually holding your hand and saying, do this, you won't fuck it up. Do this, you won't fuck it up. So if you look at any question in the testing manual. So here you go. Here's question number one, usually the usual calculation. First thing, find me the centroid. About the XX. I could say centroid about the YY. Doesn't matter. Okay? That's the first half of that table. Second, I say find me the area about the x-axis. Find it about the frickin' base. What are my DIs? All my y bars. Then I say, hey, now tell me the area moment of inertia about the centroidal. Transfer it from the base to the central. So I'm literally trying to eliminate that mathematical error of calculating the DIs between axes. Okay? And you'll see I do this all the time to you so that you will not fuck up the... There it is again. What's yours going to say? Exactly those words. Now, I may write centroid YY. I may say centroidal YY axis as opposed to XX. But that's about it. This is question number one, test number 3. Did I say it's the easiest test? Yes. Why? If you can add, subtract, multiply, and divide and understand certain concepts, you're good. Should be 100. So let's redo this exact problem that we just finished before we go by sending everything to the base. So here it is. Everything goes to the base now. Component, ICG, area, DI, DI squared, AI, DI squared. They're the same 3 pieces. It doesn't change. Doesn't change from the central. So this calculation doesn't change. Does not change. It's the same one we had here with these equations for the area moment of inertia. 472, negative 3. That ain't changing. 472, negative 3 for a total of 73. Go to your centroid, copy over the areas. What are the areas? Well, the areas were 12, 24, minus 6. Go to your centroid and give me the y bars. Because remember, I'm doing the area moment of inertia about the base of the figure. I'm not doing it about the centroid yet. What is my y bars? Somebody tell me what my y bars. Go back to the centroid. Tell me what my y bars were. I need that. Anybody got them? Come on, time's running now. What? 153. This is easy. 125, 9. Take these two numbers and please put your fingers on these two. I cannot stand it when somebody writes and gives me AIDI squared by multiplying these two columns. No, it's that column and that column. Now you have a free hand to do your calculator. 12, 600, and minus 54. Add this column up, 558. Add these two columns up. About the base is 631. Now, did I ask you about the base? No, I asked you about the central. I have the I that goes to the axis at the base. I'm now going to use the parallel axis theorem to transfer it from the base up to the central. But notice, I didn't have to sit there and figure out, oh, half of 2 is 1, 3.8 minus 1 to get the 2.8 that I got back here when I did it without going to the base. So now I say I, CG, XX is equal to I about the base minus AD squared. This is 631 minus the total area, which you know from the centroid is 30. What's my D? I need the distance between the base and the centroid, and the centroidal axis. That's my Y bar. No, it's easy. This is Y bar. That was 3.8. Guess what? 197.8 meters to the 4th. What did we get before? Oh, 197.8. But I didn't have to go through the gyration of trying to decipher what's the distance between the axis of the individual piece to the axis overall. That sucks. I've eliminated one source of error for you.